Yay!
Yay! All right, let's do another quick example. This is something that I've seen students do, and it's clever, but it's wrong. It's a clever attempt at a shortcut that's got some real physical intuition behind it. This is a clever idea, but I'll show you that it's wrong because I've seen people try to do this on tests when they're in a hurry, and it just doesn't work. And it takes a little bit of thinking to see why it doesn't work. Okay, here's the problem. Suppose I'm launching something from the moon's surface, and I want to launch it at 3,000 meters per second. All right. And then I want to find out when it's far away, how fast is it traveling when it's far away? And by far away, by the way, this is coded language for infinitely far away. That just means the gravitational potential is 0 at that point. So when it's far away, outside the moon's, practically speaking, outside the moon's influence, how fast is it traveling? Okay. Well, you might imagine that this is just another energy problem and we'd solve it the same way, which would be right. Here's the way, I'll show you the way you should solve it, and then I'll show you a shortcut that sometimes people try. And then we'll talk about why it's wrong. Okay, here's the way you should do it. Here's the right way, let's call it. I don't know. There's lots of ways you could solve these problems, but let's say that this is the right way. Okay, energy initial equals energy final, right? Just like we've been doing. EI equals EF. What that means is 1/2 mvi squared, the launch speed, minus g times the mass of the moon. We're launching from the moon. The mass of the object divided by the radius of the moon. It's from the moon's surface, so we'll put the moon's radius in there. This equals the final energy, right? And so this is going to be 1/2. We want to find this out, V final. How fast is it going when it's far away? And when it's far away, potential energy is 0. All right. That's this condition, just to make sure you see where that 0 comes from. Okay. So, well, let's cancel out these little m's. So our V final squared is going to be, let's just go ahead and write down, oops, what the V final is. It's going to be, multiply everyone by 2, it's going to be V initial squared minus 2g mass of the moon divided by radius of the moon. Okay. And if you do this, if you plug the numbers in, I did this, I get 1870. Okay, fair enough. When it's really far away from the moon, it should be 1870. Does that answer make sense? Always look at your answers to see if they make sense. I mean, yeah, I guess so, because you're launching something at 3,000, you're trying to escape the moon, right? So the moon's pulling out a little bit. So when it's far away, it better not be going faster than 3,000. That would be weird. So 1870, I don't know, maybe that makes sense. It's at least plausible. Okay, here's what sometimes people will do. A shortcut, instead of going through the algebra, what you might think you could do is this. And so let me say that this is wrong. Calculate the escape speed for the moon, because that's pretty easy, right? That's just 2gm over r. If you calculate the escape speed from the moon, I did this, and what you'll get is about 2340 meters per second. Okay, so then here's what people do, because that's a pretty simple calculation. They'll say, oh, I start with 3,000. I need 2340 to escape, so that means that V final is just the difference between those two things, right? It's just going to be, what would that be, 660. Don't do that. Sounds totally plausible, right? Until you think about it for a minute. Yeah, I mean, if velocity were like money or something, right? You have 3,000, it takes you 2340 to escape, and so what's left over is 660. So it sounds totally plausible. The problem is velocity is not the thing. Speed is not the thing that's conserved. Energy is conserved, right? So it's not the speed that you have to consider in this way. It's the squares of the speed. It's the kinetic energy that you have to consider. If you do the squares of the speed, then everything works. So that's why this is wrong. Speed is not conserved. You can't treat speed like money or any conserved quantity because it's just not. The energy is the conserved quantity. What if instead I did this? What if I did 3,000 squared? What if you try to do this with the squares of the speeds? 3,000 squared minus 2340 squared. Guess what this equals? 1870 squared. That's what's really happening. It's the squares of the speeds that's associated with the energy, right? The kinetic energy. That's the thing that's conserved. So I've seen a lot of students try this, and it's a clever idea. It's an interesting idea. It just happens to be wrong. It's just something that you just can't do because it's not right. Speed is not conserved. So whenever students do this, I try to applaud the idea. That's a very clever trick to try to solve the problem. It turns out that it's just not a valid trick. But it does show some ingenuity to even think of it in the first place. So anyway, I've seen it so often that I just wanted to address it really quickly.